The header is in this position where my knuckle is here, and you've got a B on the square, on that square. That's what we have to end up with. And we can do the same now with two transitions, two steps, using a conventional Turing machine that does not have S, the S option. It has to move. Well, we could do it something like this. What could we do? All right, we could write C here, and then move right. And I'm not quite sure about what you do with this. Can you just leave it as it is? Yeah, you could put rules that do that. Okay, so now you're here. That's after. Now you've written C here, okay, little c, and now you moved right. Let's say, and say you read D here. Well, you could have a rule that writes D back, so you don't change it. Okay, that's your first transition. So you read D and you write D, so you don't change it. And then you have a rule. If then you could replace that. If you read D, you move left, and you hold on. Okay, interesting. I'm getting. See, you have to write before you move. So I need to think about that. Okay. Yeah, I have to give that some thought, because you write before you move. Anyway, well, there's something for you to think about. So convince yourself that it can be done, that you can, with your S machine, in one move, you can end up the same way by having two conventional Turing machine transitions. Now, what if you didn't change that? If you just left it the same? Maybe that's the way to do it. Yeah, I need to give it some thought. So in your conventional Turing machine, so you leave it as it is. Or do you change it? Or so you want it to be B, so you write it as B. You do it that way. So you write it as B, not C. You write it as B. And then you move here, and you keep that the same, and then just move back. Yeah, that would work. Yeah. Well, you're thinking real time. Okay, so I think that would work. All right. Okay, so in other words, you've shown the equivalence between this S variant machine and the conventional machine. Right? You just every time you got an S in the S machine, you replace that transition with two transitions from your conventional machine, and they're equivalent. They do the same thing. Okay, so that can be done. Now that small example, it's sort of like it contains like a key idea to how to show the equivalence of two variants. So if you have two variants of a Turing machine, the answer to the question, is one more powerful than the other? Well, the strategy is to show that the two are equivalent. Right? In other words, they recognize the same language, for example, or set of languages. And so by showing equivalence is the way to answer the question, is one more powerful than the other, right? And to do that, you simulate. So you take one and you simulate it by the other. And if you can do that, they're equivalent. Right? So I guess the key word here is simulation. All right, now we pass on to an actual example of a variant, an important one. In fact, we'll do two main ones. One is the multi-tape. So the variant of the Turing machine now has multiple tapes, k of them. And the other we'll do is the non-deterministic Turing machine. branch, make copies of itself, and there's more than one next state. Very definition of non-determinism. Okay, so how does a multi-tape Turing machine work, and how do you simulate a multi-tape Turing machine? This concept important. How do you simulate a multi-tape Turing machine with a single tape Turing machine in order to prove the two are equivalent? And if they're equivalent, they have the same power. So you might think intuitively that a multi-tape machine should be more powerful because it's doing more, it's more information, more things going on. Now it will probably be a lot faster, maybe more efficient, with things going on in parallel at the same time. So more efficient, computing faster than the single tape Turing machine. But in terms of power, the actual recognition, at the end of the day, does the K tape, with K tapes, the K tape Turing machine, can it recognize a larger class of languages than the single tape Turing machine? The answer is no. They're equivalent. There's no difference in power, which is one of the main lessons of this section. All right. So how does it? Well, firstly, let's describe what a multi-tape Turing machine looks like. What is it? So now it's sort of similar to an ordinary Turing machine, okay, but it has several tapes. Well, it's sort of obvious, okay. Now each tape has its own head. Okay, so here's like my fingers. Like this is tape 1. Let's say this is tape 2, and there'll be a head, read-write head for tape 1, and there'll be a separate read-write head. It might be positioned here, and this one might be positioned here. So each tape in the multi-tape Turing machine will have its own head, read-write head. Okay, so seems reasonable. Okay, so it has its own head for reading and writing. Now now it's similar to a Turing machine. So Turing machines have an input string. So you're going to split that up, or you're going to keep it intact. You keep it intact. You put it on one, in fact the first tape. Okay. So your first tape contains the input string. Right. So initially, the input string appears on tape 1. Okay, and all the others, well, in this model, this variant, all the other tapes initially, at the beginning, are blank. They're all blanks. Okay, so that raises a question with Sipser. His multi-tape version, is he going to have a left boundary on these extra tapes? Probably, I'd say. Okay, anyway, that's a side issue. All right. Now, okay. So all the other tapes, except for the first one, they begin blank, right? Initialized to all blanks. Now, what about the transition function of this multi-tape? Well, it'll have to be changed somewhat, right? Because you're now dealing with multiple tapes, more than one tape. Okay. Now let's have this multi-tape machine. So simultaneously, right, at the same time, so in parallel, if you like, this multi-tape machine, simultaneously, it can read and it can write. So in other words, all the tapes at the same moment are reading and changing their state. Oh, wait a minute. No, take that back. There's only one state. Okay, so they're all reading or writing at the same moment, and then all shifting left or right, well, individually. Okay, so they're all reading at the same moment, or they're all writing at the same moment, or they're all shifting, if they shift, at the same moment. Okay? But still only one state at a time. We're still in the deterministic model. All right. Okay. So so simultaneously, they all read or they write or they move at the same moment, on some or all of the tapes. Okay, so the transition function now we need to modify because we're talking multiple tapes. Now you can probably see the first line of the next session here. This is what the modified, the variant transition function looks like. Okay, so set of states as usual. Now this is, remember, it's the alphabet of your tape, the tape alphabet, gamma. But now we've got k of them, because we've got k tapes. Where k is the number of tapes, right? So we may have k different tape alphabets. We'll have one alphabet per tape. Okay, that's a possibility. So you need to specify the input to your what's the word again? Transition. Yeah, the input to your transition function will be an ordered pair. It won't be an ordered pair. It'll be a k plus 1 tuple. Okay, well you can't see it, but so the input that goes to your transition function will be like qr. Well, look, I'm getting ahead of myself. I'm going to do this next session anyway. But well, let me just finish off this line. Yeah, without going into details. So whatever you're doing here, you do here, and you'll have k moves as well. You need to specify. So the transition function is telling the machine what to do next. It's specifying the next step. Okay, it'll specify the next state. That'll come from here. It'll specify what you write on the k head position. The k squares. Each square on your k tapes. So that's what this is telling you. And then for each of your k tapes, there'll be a move, a single move. Now, do you move left? Do you move right? And this is, or do you stay where you are? That's interesting. We put this in. Okay, in this variant. I mean, there are many variants, right? So a move is to stay put, stationary, S. And you'll have k of these instructions, these move instructions. All right? Okay, I'll just move straight on next session.